Now we have to study conservation laws. We have studied all the forces. We have studied different kind of forces. Now we are moving to next section of classical mechanics, that is conservation laws, where we will start with conservation of linear momentum. So before I go into this linear momentum, I'd like to discuss about something about what is conservation laws. You have to study about conservation laws. In fact, there are two approaches of solving a mechanics problem. One was through forces, like suppose if I give you a question, say like, suppose this is a question. If I want to find, suppose, what is the velocity of this small mass m when this mass comes to the bottom. If suppose the problem is, what is the velocity of this block of mass m when this block m comes at the bottom of this wedge. So this problem can be solved by using forces, by analyzing, by drawing free body diagram and then applying Newton's laws. I can solve it like this also. And there is one more approach. The other approach is to go through conservation laws. I can use conservation of linear momentum and conservation of energy to get the velocity of this body when it comes to the bottom. So that's also one of the way. That is also one of the approach of solving this mechanics problem, right? So sometimes there are two approaches. One is through conservation laws and other is through analyzing the forces, free body diagram and applying Newton's second law. So these two approaches are usually there. Sometimes conservation law gives you an alternative approach, like this can be solved using forces also and this can be solved using conservation laws also. But there are certain examples where conservation law is the only approach. Like suppose if I have a body of mass m1 moving with velocity v1 and body of mass m2 moving with velocity v2 and they collide, suppose they undergo a collision, and after collision m1 starts moving with v1 dash and m2 starts moving with v2 dash. Then in that case, here if I ask you, if I give you v1 and v2 and I ask you to find v1 dash and v2 dash, what is the velocities after collision? In that case, it will be difficult to apply Newton's second law. The reason being, here when they are colliding, they exert force on each other. That force acts for very small time, negligibly small time, and I cannot write exact mathematical expression of that force. I cannot write the exact mathematical expression of the force which these two bodies are exerting on each other. So unless I do that, I can't apply Newton's second law. I can't write Newton's second law. We have some qualitative idea of the kind of forces which is acting. The force will be very high in magnitude. The force will initially increase from 0 to very high value, then decrease from that high value to 0, and then they separate, right? When they collide, the force between them start increasing, goes to a maximum, then decreases, but then we do not have exact mathematical expression how the force is varying. So in this case, we cannot get the v1 and v2 dash, v1 dash and v2 dash, that is velocity after collision, using Newton's second law. We can't get it. We can't use Newton's second law over here. So here the conservation law is the only approach. Conservation law is the only approach. So here we will be using conservation laws. It is useful in case of collision, right? So there are certain cases where conservation law is an alternative approach. There are some certain cases where conservation law is a compulsion. You have to use conservation laws, right? So broadly, we have to study conservation of linear momentum, angular momentum, and energy. Conservation of angular momentum we will study in rotation. So here in this chapter, I'll be discussing with you about conservation of linear momentum and conservation of energy, right? We'll be studying these two conservation laws. Okay. But before I move into this conservation law, I must tell you that all of these conservation laws are ultimately derived from Newton's laws. I can get every conservation law from Newton's laws. So it's not different. It's not altogether very different from Newton's laws. Newton's laws, ultimately these conservation laws can be derived from Newton's laws in classical mechanics. So they are just, by using conservation law, we are basically indirectly applying Newton's laws. Okay. So I'll start with conservation of linear momentum. I'll start with conservation of linear momentum. Alright. You start with the conservation of linear momentum. So let's start with this conservation of linear momentum. See, linear momentum of a particle is defined as, we define linear momentum as P equals to m into v. It's a vector quantity. M is the mass and velocity is the, v is the velocity. So this is linear momentum. So for system of single particle, if suppose you have a system of just one particle, for a system consisting of just one particle, suppose you have a body of mass m, particle of say mass m, we write Newton's second law as, suppose F is the external force acting on the particle. Every force on a particle is external force. Suppose you have just one particle, system of just one particle, so if it is experiencing any force, this has to be external. So F is the force acting on that particle. F is the net force acting on that particle. So Newton's second law is written as F equals to dp upon dt. And if the force acting on a particle is 0, the force acting on a particle is 0, in that case your dp by dt is 0 and p is constant. P is constant. dp by dt is 0 and this will give you p equals to constant. So momentum is conserved. If force acting on the particle is 0, the momentum does not change. If force acting on the particle is 0, momentum do not change, right? And one more thing, sometimes your net force won't be 0. Many times this F is not 0, one of its component is 0. One of its component is 0. From here you are getting, if the force acting on the body is 0, this momentum remains conserved. Many times it so happens that net force acting on the particle is not 0, but one of its component is 0. Suppose if I write F as, suppose I write F as say Fxi, Fij and Fzk, and P as Pxi, Pyj and Pzk, then this will reduce to dpx by dt as fx, dpy by dt as fy, and dpz by dt as fz. Now if you suppose one of the component fx is 0, then this will imply px is constant, and then if the x component of the force is 0, then px, the x component of linear momentum, will be conserved. If fy is 0, then py will be conserved, and if fz is 0, then your pz will be conserved. So if one of the components is 0, the corresponding component linear momentum will be conserved. If the component fx is 0, the corresponding component px is conserved. If fy is 0, the corresponding component py is conserved. If fz is 0, then corresponding component fpz is conserved. Like this, right? So many times you come across that this complete f is not 0, but fx, fy, fz is 0, and hence the corresponding component px, py, pz will be conserved. Alright, this is how we can use the conservation laws. Now suppose if I go for system of many particles, suppose I have a system of n particles. We consider, suppose I consider a system of, say a system of n particles, say mass m1, m2, mi, mn, such that whose positions are described by R1, R2, Ri, and Rn. In that case, suppose you have a three-dimensional coordinate system like this. So this is x, y, and z. You have mass m1, m2 here, mi here, and so this is mn, right? And these are the R1, this is your R2, this is your Ri, this is Rn. They are denoted by these vectors, right? Suppose we have these n particles. Consider system of n particles, right? Then if I write Newton's law for every particle, it will be dp1 by dt is going to be F1 external, F12, F13, F1i, and this is F1n, right? F1 external is the, sorry, I'll tell you this one. F12 is the force applied by 2 on 1. F13 is force applied by M3 on 1. F1i is force applied by ith particle on M1, and F1n is force applied by nth particle on 1. So these are these are all internal forces. We call them internal forces. When do you call the force to be internal? Suppose I have considered a system of n particles, then the force which these particles exert among themselves is internal force. The force which these particles exert on each other, these particles are part of the same system. You have to choose a system. In fact, system is chosen by observer. So if I consider these n particles as one system, then the force which these particles exert on each other is called internal force, and the force which a particle from outside exert on these particles is called external force. F1 ext is not the force which the other particles exert on M1. F1 ext is a force which something else, something outside the system is exerting on M1. So that is external force. So that's very important. If I consider only M1 as a system, in that case all these forces will turn external force. So it depends on definition of your system, how you define the system. If I define M1 only as a system, then all these forces will become external force. But if I define M1, M2, M3, Mi, Mn as a system, then these forces turns internal. So which force is internal, which force is external depends on how you define the system, what particles you pick up and put in the system. So it depends on your definition of the system, which force is external and which force is internal. Similarly, if I write your Newton's second law for the second particle, this is F2 external plus F21, F23, F22 won't be there. There is no significance of F22. Second particle cannot exert force on the second particle itself. And this is F2i, F2n. dpi by dt is FIEXT, FI1, FI2, and this will be FII minus 1, FII plus 1, and you have FINE. Alright. Similarly, dP n by dt is FNEXT plus FN1, FN2, FNI, FN, n minus 1. So these are the equations. They are the equations. Applying Newton's second law on all these particles. So I can write this thing as dpi by dt equals to dpi by dt can be written as FIEXT plus sigma FIJ, where j varies from 1 to n, not equal to I. So j is varying from 1 to n. This is Fij. This is Fij. If I add all these, equations, this becomes sigma dpi by dt equals to sigma FIEXT plus sigma Fij, and Ij are all varying from 1 to n, but j not equal to I. So this is the equation in nutshell. So now here, see, for every Fij is what? The force applied by jth particle on ith particle. There exists Fji, force applied by jth particle on ith particle. For every Fij there exists Fji such that they are equal and opposite, because they are action-reaction forces. They are action-reaction forces. So for every Fij you have Fji such that they are equal and opposite, right? So here in this case, in this term, for every Fji you have for every Fij you have Fji such that they are equal and opposite. So this term will become 0, right? This term is going to become 0, and this will become d by dt of sigma pi equals to FIEXT, right? And here sigma pi is p, that is total linear momentum, the resultant or net linear momentum, total linear momentum of the system right? This is P, and sigma FIEXT is the net force acting on the system of particles. Net external force, I should write. Net external force acting on the system of particles. Alright. So I can call it F. I can call it FEXT. So for a system of particles, the resultant linear momentum is equal to the rate of change of resultant linear momentum is equal to FEXT, right? It's equal to FEXT. Now, if this FEXT is 0, it means the linear momentum of the system is going to be conserved. This FEXT may not be 0 completely. This FEXT, net FEXT may not be 0, but one of its component may be 0. Sometimes this is also the case, but many times you have the case where the resultant force entirely is not 0, one of its components is 0. I can write FEXT as FXI, FYJ and FZK, right? And P can be written as PXI, PYJ and PZK. In that case, this will break into three scalar equations. dpx by dt equals to fx, dpy by dt fy, and dpz by dt is fz, right? dpz by dt is fz. Now if fx is 0, then px remain conserved. If fy is 0, your py remains conserved, and if z is 0, pz is constant, right? If z is 0, pz is constant. So this is how this is the law of conservation of linear momentum. If one of the components 0, the corresponding component linear momentum will be conserved. Okay, v1 plus u plus mv2, this is v2, okay, so v0, sorry, so v0, so I write mv0, sorry, oh, committing lots of mistake. Okay, this was v1, last year's got changed, so today mv1 plus u, and this will remain v0. Here there was mistake line here, it will be mv0, so this will be mv0, so we'll have m plus m, and this will become v2. So this will be the good equation. So you solve these two equations, you will get v1 and v2. You solve these two equations, you will get v1 and v2. That's how you do the problem of conservation of linear momentum. These two problems are not important for exam, just for understanding how choosing a system becomes very important. How choosing a system is very, very important in conservation of linear momentum. That was the whole purpose of introducing this problem, right? Okay, thank you very much.